Hello everyone. Welcome to the fourth webinar CEPR EAERE on climate economics. I'm Christian Gollier. I'm a fellow of the CEPR, president of EAERE and professor of economics at the Toulouse School of Economics. I will chair this session. So let me tell you a few words about the event. It will last for 1 hour and a half, and it will be specifically devoted today to carbon pricing. So carbon pricing is useful to induce all CO2 emitters to internalize the climate damages associated to their emission. But even in countries without a market pricing mechanism, it's important to value carbon in order to perform the socioeconomic valuation of the myriad of climate policies that will have to be implemented in order to attain the emission targets. During this seminar, 3 panelists will summarize their findings about carbon pricing, which carbon pricing should be recommended, or about the rate at which this carbon value should grow over time. So we have 3 panelists today. Maureen, professor of economics at the University of Maryland and senior fellow of Resource for the Future. Michael Greenstone, professor in economics, University of Chicago and research fellow of CEPR, and eventually myself. So there will be 3 presentations of 20 minutes each, followed by a discussion. So if you have any question related to this event and to the contents of this presentation or anything related to carbon pricing, please use the Q&A button at the bottom of your screen, and our moderator today will collect them and organize the discussion at the end of the presentation. So let me mention that Rick van der Ploeg has accepted to be the moderator today. He is university professor at Oxford University, professor of economics, and also a fellow of CEPR. So without any further comments, let me switch to the first presentation by Maureen. Maureen, the floor is yours.
Thank you. Let me just get my presentation up here. Thank you for asking me to speak today. Since 2010, the US government has calculated the social cost of carbon. That is the damages from emitting a ton of CO2 into the atmosphere. The current interim value of the social cost of carbon is about $50, 43 euros a ton. What I'm going to talk about today is how the US government arrived at this figure, how it's being improved, and why I believe it's important to calculate the social cost of carbon. So first of all, there are 4 steps involved in calculating the social cost of carbon. If you emit a ton of CO2 into the atmosphere today, some of it will be left centuries from now. So it's necessary to describe what the world is going to look like in terms of population, GDP, and in fact, the future emissions of CO2 and other greenhouse gases in order to calculate climate damages. So what I've shown here in this first step is these projections from roughly the present to 2300. After you've made that projection of a path of CO2 emissions, you've got to calculate what impact that is going to have on mean global temperature and also on regional temperature, on sea level rise. You've got to do this first for some baseline path, and then you'll add a pulse of CO2 to that path. And what the middle diagram here is showing is the impact, really the change in temperature and other impacts that are occurring because of the pulse. These are going to lead to a change in climate damages. So climate damages include impacts on agriculture, on human health, on energy, and so forth. Hopefully you can monetize these damages, and you would look at the change in those damages associated with the pulse and aggregate the damages across countries. And then finally, in the last step here, in step 4, you have to discount these damages to the present. So here are the 4 steps. The US government began to calculate the social cost of carbon in 2010. Barack Obama established an interagency working group. The group continued working from 2010 through 2016. Unfortunately, when Donald Trump became president, he disbanded the group, but it has been reconstituted recently by President Joe Biden. In fact, it was the first thing he did it the first day he was in office. What I'm going to show you are what the interagency working group came up with as of 2016, which are currently the interim values that the US government uses. So here's what the IWG did. They took results from 3 well-known integrated assessment models, DICE, Fund, and Page. They imposed on each of these models the socioeconomic projections that I spoke of. They took 5 projections from the Stanford Energy Modeling Forum. They assumed they were equally likely. They imposed a common distribution over equilibrium climate sensitivity in the climate part of each of the IMs. They also preserved the uncertainty in the parameters in the climate and damage parts of Fund and Page. So they then ran 150,000 Monte Carlo runs, 50,000 for each model, using 3 discount rates, 2.5%, 3%, and 5%. And what I'm going to show you on the next slide is the distribution of the social cost of carbon for each of these discount rates. Okay, and these are the numbers that are currently the interim numbers for the US government. The values here are all in 2020 dollars, corresponding to emitting a ton of CO2 in 2020. So the green bars show you the distribution of the social cost of carbon when you use a 5% discount rate. The blue bars correspond to a 3% discount rate, the pink to a 2.5% discount rate. You can see that the social cost of carbon has a longer tail rather, the lower the discount rate, and also a higher mean. The number that has been focused on is really what happens when you use a 3% discount rate. In the US, that is one of the official discount rates to be used in benefit cost analysis. It's quote unquote the social rate of time preference, and that leads to the $51 number. Okay, the estimates that I just showed you and how they were, how shall I say it, arrived at, raise 4 questions. The first is, when you're projecting what's going to happen in the future, what assumptions should you make? And also, how likely is each possible future scenario? Could the climate portions of DICE, Fund, and Page be improved? We'll see that the answer to that is definitely yes, but that's a question that these estimates raise. There's also the issue of the damage estimates underlying the versions of DICE, Fund, and Page that went into the estimates on the previous slide. Fund and DICE are based on the literature from the 1990s. There's been an explosion of research on climate damages that just isn't reflected in the estimates that you saw. And finally, we come to the difficult question of how damages should be discounted to the present. Should we really use a constant exponential discount rate? So what happened was, in 2016, the IWG themselves came to the National Academy of Sciences, and they asked the National Academy to put together a committee to give them advice really on how to answer these questions. I was fortunate enough to co-chair this committee along with Richard Newell, currently the president of RFF. And what we did was to come out with a report answering these questions. Unfortunately, it was released the week before Donald Trump was inaugurated, but nonetheless, the report has important content and people have followed up on it. So our main message was don't just use these already composed integrated assessment models. Put together your own analysis by unbundling the 4 steps of the analysis that I showed you on the first slide, the socioeconomics, the climate part of it, damages and discounting, and have relevant experts weigh in on each of these portions. That's really what you should do. And of course, given the considerable uncertainty at each stage, you've got to quantify it, pass it to the next stage, and generate a distribution of social cost of carbon values. So the report also said the following. In the short run, it should be possible to update the social cost of carbon using statistical methods and expert elicitation in the first stage of the analysis to project for future GDP, population growth, and emissions. In terms of the climate portion, you should use a simple Earth system model. The well-defined diagnostic tests were actually specified by the climate scientists on the panel, and they developed a model with the acronym FAIR. And I'll talk a little bit about that later. You obviously do need to update the damage calculations for reasons I've already mentioned. And importantly, our suggestion about discounting really broke with the standard US practice of using a constant exponential discount rate. We said you want to use a discount rate that more or less obeys the Ramsey formula. That is, in scenarios where economic growth is high, we are going to discount the damages to people under those scenarios when they're doing really well at a higher rate than we would discount damages in states of the world where economic growth is slow. And I will be saying a lot more about this in a minute. Okay, so what's been done to really implement these 4 suggestions? And that's what the rest of my talk's about. So in terms of the socioeconomic trajectories and emission paths, Resources for the Future undertook a really huge project, bringing together dozens of researchers. I must say, in full disclosure, I was not part of this project, so I'm looking at it from the outside. It was a fantastic project. The results were announced earlier this month, and you can find them on the RFF website. But what was done with regard to socioeconomic trajectories was, in the case of population, to extend the UN's statistical model to 2300, but to modify this using expert elicitation. In the case of economic growth, a paper by Mueller, Stock, and Watson, which uses data for 118 years for 113 countries to estimate an econometric model of the joint growth of national per capita GDP over the long run. That model was augmented also by formal expert elicitation. And in the case of emissions paths, 10 experts were asked to come up with their recommendations, conditional on each possible economic growth scenario. And again, there was a probability assigned to each of these future scenarios. You'll see the results of some of this later. In terms of the climate part of this, I think one of the main messages that has come out is how fast a pulse of CO2 affects mean global temperature. So what you're seeing in this diagram on the vertical axis is an increase in mean global temperature for a 100 gigaton pulse of CO2. Time is on the horizontal axis, goes out 200 years. The red line on the graph, which says best available climate science, suggests that the peak impact of this pulse is going to be felt within 20 years when it's emitted. And this is contrasted with the corresponding assumptions in Page, Fund, and the 2016 version of DICE, which has these peak impacts occurring much later. with any positive discount rate, and the box at the bottom of the diagram is showing you the present value of $1 discounted at 2%, there is going to be a bigger impact in terms of climate damages, with damages occurring sooner. In terms of updating the damage literature, what you're seeing on this slide on the left-hand side is the publication dates of the papers that went into the versions of Fund, Dice, and Page used by the IWG. So it's the number of studies on each vertical axis. Time goes from 1986 to 2020, and you can see that the publication dates of the damage information really is, for the most part, in the last century. This can be contrasted with the graph on the right-hand side of the slide, and this is actually the result of a review of the literature by the Climate Impact Lab. Again, on the horizontal axis, you see time from 1986 to 2021, and the vertical axis goes all the way to 70 studies. You can see that there literally have been hundreds of studies that have been published estimating climate damages. The literature is just exploding, and indeed, there is a lot to be done in terms of changing the damage estimates in underlying the social cost of carbon. Okay, now we come to the, I would say, difficult part of things, to discounting. So here's what the committee recommended. We said, look, each of these socioeconomic scenarios is going to generate a path of growth rates. There's a probability associated with the scenario, and then there's going to be, for each scenario, there'll be a path of growth rates from the present to 2300. Let GT be the average rate of per capita consumption growth from the present to time t. We recommended that what you do to discount damages in year t is to use a discount rate RT, which equals delta, the pure rate of time preference, plus eta, the absolute value of the marginal utility of consumption, times GT. So what's going to happen here, as I said a few minutes ago, in scenarios where the economy is growing fast, we are going to be discounting climate damages higher, at a higher rate than we would in scenarios where the economy has been growing more slowly. This approach is also going to take care of the correlation between the discount rate and climate damages, which Christian has written much about, the climate beta. Damages will also vary with the growth rate of per capita GDP. And F prime could be positive if there's a positive climate beta. It could be negative if F prime is negative. But that correlation will automatically be taken care of by using this formula. This raises the really difficult issue of, how do you choose delta and eta? One way is to make sure that the RTs in the next few years match observed market rates. It's also true that compared to constant exponential discounting, this is going to reduce the variance in the social cost of carbon across scenarios. So what I'm going to show you are the results of using this discounting approach. And again, this is all contained in a paper that recently was published, or a working paper recently released by RFF, which you can find on their website. So the values of delta and eta have been chosen so that the near-term rates match alternately 3% and 2%. And what was done here was to take the RFF socioeconomic projections that I just spoke of. For each of the socioeconomic projections, they are translated into impacts on temperature using a version of the FAIR model. The damage component of the estimates you're going to see in a minute come from the 2016 DICE model, so they have not been updated. And you're going to see the results of discounting. And the term stochastic discounting is used because for each of these possible future paths, we have different GTs or GT streams, and each is uncertain. So they use the term stochastic discounting, and you'll see the what happens when you pick delta and eta to match the 3% near-term rates versus the 2%. Okay, so what you're seeing here in, I guess it's sort of a bluish distribution, is the distribution of the social cost of carbon, again, emitting a ton in 2020, when you key the parameters in the Ramsey model to 3% near-term rates. The mean of that distribution is $56. When you key the near-term rates to 2%, the purple distribution arises, and the mean of that distribution is $171 per ton of CO2. Once again, I should emphasize that this is all based on the DICE model for calculating damages. The DICE model has a climate beta of 1, so you'll be discounting climate damages perhaps more heavily than you might when the damage component of the analysis is updated. I think my time's just about out. So let me say in closing that I think it's very important to compute the social cost of carbon. I know that a lot of people in this audience believe that the way we should price carbon is to set a climate goal, to figure out what the marginal cost of achieving that goal is along an optimal path. In other words, to set target consistent climate prices. I would emphasize that indeed it's fine to set a temperature target, but implicitly you are making judgments about damages and the value of avoiding them. All of the uncertainty associated with climate impacts and climate damages that we've spoken of are not really avoided by setting a temperature target. When you calculate the social cost of carbon, you are forced to make these judgments and uncertainties explicit. I also think that it's important to calculate damages, and I think Michael Greenstone would back me up on this, to make the impacts of temperature targets real, to make them real to people who are in Bihar, India. What's going to happen there if we don't achieve the temperature targets? This does provide support, I think, for mitigation measures. Also, when you're measuring damages, you'll get estimates of the benefits of adaptation. And I must say that if you're going to do a benefit cost analysis of projects to reduce CO2 emissions, you want to measure the benefits of reducing those emissions, and that is what the social cost of carbon measures. I will stop there.
Wow, thank you very much, Maureen. This is really bright. I have many paper to read for the weekend. In particular, the last one you mentioned, the one summarizing what you presented at the end of your presentation. So without further comment, let me immediately switch to Michael. Michael, you have the floor.
Maureen's talk was terrific as always, and when she announced that that's what she wanted to cover, I thought what I would try and do was complement what she was doing by stepping back a little bit. And I know we're supposed to be focused on carbon pricing, but I want to put, I guess, a rock in my shoe is that I don't really think we should think of the climate problem. And I know that might sound slightly jarring, but really I think what we should think of as the global energy challenge. And then I'm going to try and relate that to pollution pricing. And I think the global energy challenge, which better captures the full nature of the problem, is that societies around the world have to find a way to balance between 3 different goals. The first is how to have inexpensive and reliable sources of energy. And I want to thank Christian for organizing this event to happen exactly at the point when there appear to be energy shortages in Europe and very high energy prices. There was a remarkable foresight, as always, from Christian. And that's a really important goal, and societies are extraordinarily focused on that with good reason. And the second goal is, well, how can you achieve that without having severe local pollution problems? And this is a picture from Beijing, maybe 7 or 8 years ago. And it's the middle of the day and you can't see the sun. And I'm going to come back to the picture in a second. And then the third leg of the stool that I think societies have to balance is, well, we need inexpensive and reliable energy. We want to avoid local pollution problems. And how do we avoid disruptive climate change? And the three are interconnected. And I don't think that you can think about one of those questions, say climate change, without seeing that full picture. And inevitably, that means that there's going to be trade-offs. It's not hard to think of policies that are very good at attacking one of those goals. But to find one policy that beneficially moves the ball forward on all three of those goals at once is very, very difficult to identify. And so just the picture that I wanted, why I think this conveys it so well, is, in the picture, you can just viscerally feel the economic progress that has characterized China in the last 30 years. And you can see this guy on a bike is going to be in a car very soon, and the guy in a car is going to be, was probably in a bike not that long ago. And all of that has been unlocked by access to inexpensive and reliable energy. As I mentioned, the air pollution is, tangible in this picture. It's no secret to the guy on the bike. Wearing a mask. This is pre-COVID. He's got goggles. And so the same energy sources that unlocked all this growth and produced all this pollution are, of course, also increasing the odds of disruptive climate change. And so that's going to be the theme of my talk, that how do we, the climate problem is not, in my view, the right way to think about it, but the global energy challenge is the right way to think about it. And then I'll try and put carbon pricing into that picture. Okay, so the way I'm going to try and get there is to go through quickly 7 facts that explain this difficult balance between energy and growth. I love figures, and this is like, data is so often disappointing in the sense that there's some feature of it that does not fit our explanation of the world or our view of the world. And yet this is a rare example where it works out perfectly. There's no path to high levels of GDP without lots and lots of energy consumption, at least in the historical record. And you can see this here. So energy is going to be critical for growth, and countries are going to want to continue to use lots of energy. The second fact is, although it is not true in Europe, and although it is only temporarily a problem in Europe, I think, and it is not really true in the United States, energy access is an extraordinary problem across the world. Certainly, if you view it from the vision of a randomly chosen person on the planet. So in the United States, per capita electricity consumption is about 13,000 kilowatt hours per year. In China, it's like maybe 5,000. In India, it's which has 1.4 billion people, it's maybe about 1,200. Maureen mentioned the state of Bihar, where I do a lot of work. There's about 120 million people there. Their average person in Bihar is consuming about 200 kilowatt hours per person per year. Totally unacceptable state of affairs. In Bihar, they're not thinking like, hey, this is fine. We don't really want to be like Europe, and we don't really want to be like the US. They're desperate for growth. Same with the rest of India, and even China, I think, which is now, not such a poor country. There's probably still more energy growth ahead for them. So it should not be surprising then that fact 3, that demand is projected to grow very rapidly in today's developing countries. Here are developed countries, think of them as like the OECD, and this is emerging countries, and there's just going to be expected to be very, very sharp growth in energy consumption in those parts of the world. Okay, and so that's all well and fine, except for one, which is energy is critical for growth. Developing countries, today's developing countries are going to want a lot more energy consumption. But the challenge is that the standard projections to have fossil fuels are expected to meet much of this growth. Now, this is a little dated. I went back and forth as to whether or not I should use the 2018 or the 2020 IEA report. The 2020 only goes out to 2030, so this is probably understating the expected role of non-fossils, since there's been the rapid declines in the price of renewables. But I think the point stands, which is today fossil fuels for world primary energy demand account for about 80% of total energy consumption. By 2040, even despite all the headlines about the floating in the ocean, or soon maybe floating in the sky, wind turbines, or some other really cool creation, fossils are still expected to account for 72% of energy consumption in 2040. And it's probably a little bit lower with the updated data. And so why are fossil fuels projected to continue to have this stranglehold on energy supply? Well, it varies from situation to situation, but this is for the United States. And here I put a dot. The red line is the levelized cost of energy. So that's the cost of producing 1 kilowatt hour of electricity from a new plant that would come online in 2024. And with today's natural gas prices, I'm 2 months behind, so I haven't captured some of the increase. It's about 4 cents per kilowatt hour. In existing coal plants, that's like a plant without environmental controls, which really don't exist in the United States anymore, but do exist in many other parts of the world, is about 3 cents. A coal plant in the United States with all the doodads of environmental controls is probably 7.5 cents. And a nuclear plant, no one really knows because we can't build nuclear plants in the United States anymore, but a placeholder might be about 9 cents. Okay, so that's what the fossils can do. And you should think of the price of natural gas as the outside option all the time. Now what I've done, and it's imperfect, but I have built Frankenstein plants. And what do I mean by Frankenstein plants? These are plants that solve the intermittency problem of renewables. And so this is a wind onshore plant with natural gas backup, peaker plant on the side, solar, and wind offshore. And just what I want you to take, and I'm going to do the same thing over here for battery backups. And what I want you to take away from this, and by the way, of course, with natural gas backup, they're continuing these fossils. What I want you to take away from it is the low carbon energy sources cost more. It's not a deep point, but it is, an inescapable fact. We are hoping things change, but that's the way it is. And now I just want you, and I'm going to keep coming back to this, put your head back in India, put your head back in Bihar. Like, what is true there? If the world is going to decarbonize, you're effectively asking not Oslo, not London, not Washington, D.C., not Detroit, to buy more expensive energy. You're asking Bihar, India, which has got 200 kilowatt hours per person, to buy more energy. Now, maybe out of the goodness of our heart, the rich country's heart, there'll be bags of money shipped over there, but that's a very, very challenging political campaign to run. So anyway, in the power sector, we're projected to continue to heavily rely on fossils because of this, because electricity markets do not account for the carbon costs, and I'm going to come back to that. The same thing is true in transportation. This is a graph I've made of an electric vehicle with 250 miles of range. Today's estimate of what a battery pack costs, oil would need to cost about $150 for the lifetime cost. This red line is the equal cost line. For the lifetime cost to be equal between the electric vehicle and the internal combustion engine. if we went to today's WTI crude price, battery prices would have to be about half of what they are. So we're just not there yet in transport either. There are, of course, electric vehicles being bought. They're often bought with subsidies. And so the way we have structured markets where prices do not reflect the externalities continues to push us to use fossil fuels. And that's why those numbers point in that direction. Okay, so fine, we're going to use fossil fuels. What's so bad about that? Well, there's two things that are really bad about it or challenging about it. Fossil fuels increase pollution, and that shortens lives. And by pollution, I mean local air pollution. Think of it as particulates air pollution. So if you take not the recently updated WHO guideline, but the one from a year ago for what is safe for particulates pollution, you have 6 billion people currently living in areas that exceed the 2020 WHO safe guideline for small particulates. A lot of them are focused in Asia and in Africa. And this is from something that I've created called the Air Quality Life Index. If you put it all together and took some of my research on what the impacts of air pollution are on life expectancy, what you would find is that the average person on the planet is living about 2.2 years less due to particulates air pollution. And so I like to say this, and I think it's true, even though we're thinking about climate all the time, is that particulate matter air pollution is the single greatest threat, external threat to human health. Is there anything else on the planet that robs the average person on the planet of more than 2 years of life expectancy? Well, it's not smoking, it's not alcohol and drug use, it's not unsafe water, it's not road injuries, HIV, AIDS, on and on and on. So that's a downside of fossil fuels. The sixth point is that fossil fuels are causing climate change. And as a friend of many of us on this Zoom, Marty Weitzman used to say, climate change is the problem from hell. And it's the problem from hell because its projected impacts are large, and I'm going to emphasize this, very heterogeneous around the planet. And so this is something that comes from some of my work on combination of my work in the United States and India. This is the impact of swapping a day from 70 to 74 degrees to any of these other temperature bins. And I apologize, Americans, including myself, are very poor at Celsius, so this is in Fahrenheit. And you can see the hot days do kill people, as is well understood. But now I'm going to do a little trick. I'm going to stretch out the y-axis. So that same blue line is here. You can see the uptick at the high temperatures, but it's very flat. Why did I stretch it out? Because now I'm going to put the response function of India on here. And look what happens in hot days in India. It's about 20 times worse than a hot day in the United States. And I want to connect this to the global energy challenge. So if you're in India, the red line is awful. The red line is, early death, disease, like all kinds of terrible things. And you're looking at the blue line in India and you're like, well, that is not cool. I want to be on the blue line. And what is, and not just I want to, I need to be on the blue line. And what is the best way to get to the blue line? It's lots and lots of growth. And I'm just going to come back to, well, that runs counter to buying more expensive energy. This is from some work that I've been doing with the Climate Impact Lab. It just highlights that the expected damages from climate change, so this was current from climate change, are vastly different around the world. Oslo, there's expected to be great reductions in mortality rates because you're getting rid of all the cold days that kill people. And Accra, by contrast, an enormous increase in mortality, and it varies around the world. And it just emphasizes, and this is, I'm going to, bastardize Marty Weitzman problem from hell. He meant it in a slightly different way, but how are you going to get people who see the world so differently and see the impacts of climate change so differently to come to an agreement on, and now I will make fun of Christian, he didn't really say this, but I'm imagining as a good European, he must think that there should be a uniform global price on carbon around the world. And how are this disparate set of people going to come to agreement about that. I'm going to skip this for the interest of time. And now let me just try and drive this all the way across the finish line about these trade-offs. Here is the annual greenhouse gas emissions by region. This is not historical. This is just annual. So this is 2020. You can see the U.S. is about 15%. And it's projected to go down. The other developed countries goes down by 2050. That certainly includes Europe. And here's the end of the century. So if the planet is going to do something about climate change, it is absolutely critical that there be reductions in today's developing countries. And what's the problem with today's developing countries? Like they're the ones, because of this global energy challenge, who are desperate for more energy consumption and are desperate not to pay too much for it. So some way, somehow, if we're going to do something about climate change, the bars can't go up like that. Okay, and I'm trying to be respectful of time here. So, you know, the climate challenge is substantial and the global energy challenge makes it harder. Like, I'm always daunted by this graph. There's a version of this for 1.5C as well. You know, here we are with energy consumption out to, let's call it 2020, maybe it's 2019. And if you really wanted to comply with 2 degrees, these are the cuts that would be necessary. You know, I think it's probably the less I say, the better. It is. So first of all, I was able to get that into C, so I feel like I deserve, as an American, some credit for getting out of F into C. But it's just a daunting graph on what's going to be asked for the world. So now my kids tell me that, well, gosh, Dad, that's like totally gloomy talk. Do you have something to say at the end that isn't so gloomy? And so I'm just going to come back to the theme of this session, which is about carbon pricing. And it's a reminder, when there are really 2 market failures here, and we know what to do when there's market failure, these market failures, and there's 2 standard policy solutions. So the first is we need to price energy at its full social cost. We're using all those fossil fuels because we've constructed energy markets in a way so that they push us to use fossil fuels. So it shouldn't be surprising, because externalities are largely not priced. And so I'm going to come back and just flip this on its side to the levelized cost of energy for new plants in 2024. We saw this before in a different way. Natural gas is about 4.2, an existing coal plant is 2.9 cents. A nuclear plant is 9 cents, and a new coal plant is about 7 cents. Okay, so we've constructed markets so that we will continue to use coal and natural gas. That's a statement about the world, not about an individual country. Here are our guys with renewables and natural gas backup, and here are the renewables and battery backup. You guys already saw this. Now I'm going to do a trick. Be prepared. I'm going to introduce a carbon price. And the first carbon price I'm going to introduce is the Biden administration's interim social cost of carbon, which Maureen talked about. It's just a carryover from Obama. And see, well, does that change the playing field at all? Because I'll just note, right now, no one would ever buy nuclear. And, you know, to a first approximation, no one would really want to buy these things if it was a pure cost. Okay, so that's what these green bars do. They're amazing, what carbon pricing does. It takes coal, and its coal is out of the money. No reasonable person would say, hey, with full cost, coal looks like a good deal. And this is at $51 a ton. And suddenly you find natural gas is still like a winner, but you find wind onshore seems competitive. The reason there's a green bar, remember, is this is a natural gas backup. But maybe wind onshore with battery backup is almost competitive. And then I'm going to do one more twist here. I'm going to not undertake all of the important things that Maureen outlined about how to fix the social cost of carbon. I'm just going to tweak one thing. I'm going to change the discount rate and turn it from 3% to 2%, because that the international global capital markets have changed in the last several decades. And when you do that, without even taking on all the other important things that I think, and I've been working on, need to be done to social cost carbon, what happens to the playing field? So here I'm going to go to $125 a ton, which is 2% discount rate. And, you know, coal's going to stay in the ground forever with that. No one's using coal. It's like 18 cents a kilowatt hour, even if you don't have environmental controls on it. Natural gas is 11 cents. Suddenly people, at least in the United States, are going to start building nuclear plants. The renewables start to look a lot better, renewables and batteries. And it just highlights the transformative effects of pricing externalities, which I took as our charge from Christian. And now as a favorite thing, since I think we don't pay enough attention to air pollution, I'm just going to add another line to this for if you monetized you charge fossils for their health effects associated with particulates air pollution. And when you do that, coal's, you know, really staying in the ground. No one's digging it out. Nuclear looks like not such a crazy technology, and these other technologies look much more in the money. Okay, how are we doing? With all due respect to my European friends who are not like the rest of the world, we're doing terrible on carbon pricing. The average ton of CO2 around the world faces a price of about $2.50. 16% of carbon emissions face a price that's above zero. So I'll just leave it at that. How is the US doing? We love a wide set of incoherent policies, and we find carbon pricing to be distasteful and un-American. And so instead we do all these things. I'll just note they're all mostly more expensive than the Obama social cost of carbon. They're way more expensive than the regional cap and trade prices that we have. But we like those expensive ones and incoherent ones that pick off parts sector by sector. And then I'm going to close because I know I'm overboard. I'll just note we're not investing in R&D like finding low carbon energy sources is super important. And you can see this in kind of global spending on energy R&D. The Biden administration is trying to do something about that, but we're not currently doing that. And I'll just close with our guy on the bike. I think and I'm going to, just to be provocative, say it's not the climate challenge. It is the global energy challenge. And why it is so challenging is it looks so different. In every part of the world, it looks different than some other part of the world, because the trade-offs that people would have to make depend on local conditions, like the local climate. It depends on how wealthy a place is, depends on their access to local energy sources. And it's why I think it's just such a terrific and awesome area for research and for policy, which is trying to find some balance between these three goals in this very disparate world. Is such a great challenge. So let me end with that and apologize for going long.
My paper is related to what Maureen said at the end of her presentation, saying many people switch from first best optimality, comparing marginal cost and marginal benefits of the abatement effort, and that lead to an optimal objective, could be 3 degrees Celsius, 2 degrees Celsius, and an optimal schedule for pricing carbon. But the truth is this holy grail of first best carbon pricing does not correspond to the real political debate right now. Right now, we have a 2 degrees Celsius written in the Paris Agreement, and many countries have decided to put a quantitative target. So Europe is accepting the 2 degrees Celsius, trying to go to zero net emission by the year 2050, and many other countries are trying to do or to commit on the same thing. So we are moving away from the first best cost benefit approach to cost efficiency, where we have either a target like 2 degrees Celsius, and so that corresponds to an intertemporal carbon budget available for the next 2 centuries of emissions, emission possibilities compatible with the temperature target. Or we could even go to a third best approach, cost efficiency approach, what I call cost efficiency approach number 2, where we do not even try to optimize the schedule of the effort over time, where we decide that it will be 25% reduction, 55% reduction by the year 2030, and zero net emission by the year 2050. That's third best, and we don't know whether that's optimal or not. And that's basically the question I will raise in this presentation. So what I examine in this paper, I examine 2 related questions. Question 1, in this cost-efficient approach number 1, what is the optimal rate of growth of carbon price? Should it be 2%, 3%, 4%, 8%, whatever? That's the first question. That's really the objective of this paper. And related to that question, one side result is if once we have determined the optimal growth rate of carbon price, we can determine whether this 55% reduction by the year 2030 for Europe is optimal or not. So the main result as a preview of the result is first the optimal growth. In my paper, given the calibration of my model, I obtained an optimal growth rate of real carbon price at something like 3.5% per year. And that implies that when you compare to the existing models and the existing recommendation in the literature, in this literature, most often the growth rate of the carbon price is much larger than that. And that suggests that there is a waiting game still going on in this model. So people are providing this recommendation with a very large growth rate of carbon price are also playing the waiting game. Let us postpone the effort to the future. So we are procrastinating. Lydia, could you switch? Okay, so very quickly here, so you see if we have a carbon budget intertemporal, if we decide to increase the growth rate of carbon price, I mean, that will allow us to do much less today and having a smaller carbon price today. And that's what I believe is happening these days in many different circles, academic circles and political circles. Lydia? Next slide. So here is an example. UK as a shadow price for carbon starting today, going up to 2030 exactly. And so you see at the central, if you take the central approach, the central number, you see a price of carbon that grows very rapidly from today to 2030. In fact, when you compute the growth rate, it's 15%. 15% per year growth rate of real carbon price in the UK. Next slide, Lydia. So this is, I was very shocked by this. I went to the IPCC fifth report and I collected the calibrated models of the IM models that are compatible with the 2 degrees Celsius. And I got something like 356 models or calibration of those models. And I just look at the growth rate of carbon price between 2020 and 2050. And I get here the distribution of the growth rate of carbon price. And just, you see, this is very diverse. There is a lot of diversity in the growth rate of carbon price over the 30 years period. But the mean is almost 8%. It's 7.9% per year growth rate of real carbon price. So I was also shocked. And then, in fact, Lydia, next slide. Then, in fact, I started from the French case. The French case, there was a commission that met in the year 2017 and 2018, named Commission Alain Kinetou. And this commission went using a cost efficiency approach, trying to determine what price of carbon is compatible with the French objective of 2 degrees Celsius. And so they came out with a carbon price for the year 2020 of 60 9 euros per ton of CO2, growing up to 775 euros by the year 2050. And that's an 8% growth rate of carbon price again. So you see there is a common, when I look at all those models, cost efficiency approach, they suggest a very low carbon price today, a relatively low carbon price today, and a very large carbon price in the future. And this very large carbon price in the future is indeed necessary to say, we don't do too much today, but in the future, we will do a lot with this very large carbon price. Okay, next slide. So what should the carbon price, the growth rate of carbon price be? Well, if I go back to this French example where they say it's efficient to have a carbon price today of 69 euros per ton of CO2 and having a 775 euros per ton of CO2 carbon price in 30 years from now, meaning you should be, because price is marginal abatement cost. So if we have intertemporal carbon budget for France, we should be indifferent at the margin between reducing emission today by 1 ton or reducing emission by 1 ton in 2050. So if I front load the effort, moving the effort to reduce by 1 ton by the year 2050 to reducing it today, the costs of that front loading effort is 69 euros today, and the benefits in the year 2050 is I will save the marginal abatement cost, which is 775 euros. What's the rate of return of that front loading effort? It's 8% per year. So you see, should we be ready to be, should we be really indifferent between spending 69 euros today or 775 euros in the year 2050? Well, it really depends upon what's your discount rate. And going back to the comments raised by Maureen earlier, 8% is certainly not a good idea as an answer to the question of what's the socially desirable level of the discount rate. We almost, I think, universally believe it should be smaller. So again, in fact, I'm talking here about the Ottmar rule. When you have an intertemporal carbon budget constraint, it's like an Ottmar problem. How do you allocate this effort to stay within this budget? Well, to test whether your trajectory is efficient or not, your trajectory of effort is efficient or not, you should look at the value of your effort, and that's a carbon value. So under the Ottmar rule, we all know that the growth rate of the carbon price in this framework should be equal to the risk-free discount rate, which is clearly much smaller than 8%. So if I would stop here saying in this world with no uncertainty, the carbon price should increase at the risk-free rate, which is clearly much smaller than the growth rate of carbon price I observe in all those models. All those models propose a price of carbon today, which is way too small, and compensate that with a very large promise of a large growth rate of carbon price. So this is inefficient, that's a waiting game. However, of course, in this problem, uncertainty is very important. It's clear that nobody knows today what will be the green technologies available in 2040 and 2050. And then here we should go back to the last slide by Michael. There is a lot of uncertainty about what will be available at that time, what will be the price to produce 1 kilowatt hour using wind or using coal or using solar, in particular, given the intermittency and the problem of storage of electricity. So nobody knows exactly what will be the price. And one issue is maybe the carbon price should be low today because we believe in that in 20 years and 30 years from now, we will have technologies to produce energy at a cost which is not larger than today. But it's a big bet. Huh? It's a big green bet, as I used to say. Lydia, next slide, please. So there is a lot of uncertainty associated to the future marginal abatement cost, and therefore the Ottmar rules cannot be used per se. We need to take into account of this uncertainty. There is uncertainty due to green technologies, green innovation. There is uncertainty about economic prosperity in 30 years from now. Maybe the economic growth will be very large, and therefore we will, in the business as usual, we will emit much more than expected, and therefore we will have to implement a much stronger abatement effort that will be have a much larger marginal abatement cost, and so on and so on. So economic prosperity, uncertainty about that translate into uncertainty about what will be the marginal abatement cost. And so again, we cannot use the Ottmar rules in that framework. So just to give you the idea, the main idea of the paper here is suppose that this uncertainty is such that there is a negative correlation between the marginal abatement cost and the future prosperity, let me say future consumption. In that case, under this assumption of a negative correlation between marginal abatement cost and consumption, well, the situation is quite bad. You see, the worst scenario in terms of green innovation will materialize when at the same time I have a long recession in our economies, and therefore it makes climate change problem and the energy transition much more problematic, and that probably should induce us to do much more effort today than we would do under certainty. And so that suggests that if we have this negative correlation, we should have a much smaller growth rate of carbon price in the future and a much larger carbon price today. So that's the idea. What I want to do here is to adapt the Ottmar rule to determine what's the efficient growth rate of carbon price in expectation when I face all those uncertainties. And the idea is that if I have negative correlation between marginal abatement cost and growth and economic growth, I should have a growth rate of carbon price in expectation, which is smaller than the interest rate. And reciprocally, if I have positive correlation between the marginal abatement cost and future consumption, the carbon price should grow at a rate which is larger than the risk-free rate. And that may justify going up to 8% growth rate of carbon price. That's the question I examine numerically, quantitatively in the paper. Lydia? So just to give you, well, that's, yes, to give you an idea of the uncertainty we face about the future marginal abatement cost, this is coming from the same data set from the IPCC fifth report. Here I described the distribution of marginal abatement costs by the year 2030, seen from 2015, the date of publication of the fifth report. At that time, what was the expectation about the marginal abatement cost, the distribution of the marginal abatement cost by the year 2030, given an objective of 2 degrees Celsius? And you see here a large window of possibilities about marginal abatement costs. Some models say a very low carbon price will be enough to solve the problem, and others say it will need, even by the year 2030, a much larger carbon price of €300, with $300 per ton of CO2 of dollars of 2005. Lydia? So in the paper, I do different things. I have basically 3 models. I will consider only one in this presentation, given the lack of time. I have 5 minutes to go to give you the answer to the question. Here, I will calibrate a 2-period model with macro uncertainties. So here is the model I want to discuss here. So my model is as follows. I have 2 periods with uncertainty about the TFP, total productivity factor, about the marginal abatement cost function, and about the carbon budget. So, and here what I want to do from this model, I want to determine simultaneously the equilibrium risk-free rate, or the efficient risk-free rate, the efficient risk premium, okay, and the efficient carbon price. okay, or the efficient growth at the same time the carbon price today and also the growth rate of the expected future carbon price. So I want to combine these three things together because I want to have carbon prices that are compatible with the price of other assets in the economy. As I explained earlier, you know, this 8% growth rate of carbon price is just incompatible with other price of asset in the economy, in particular risk-free bonds. Okay, so I want to combine to have the three all together: the risk-free rate, the risk premium, and the carbon price, the growth rate of the carbon price. So I will not go much into the details. I optimize in this model. I optimize the effort today and the carbon that give me the shadow price of carbon and also the carbon price in the future. So next slide, Lydia. So remember, the theoretical result is the carbon price should grow at a rate which is larger than the risk-free rate if there is a positive correlation between the MAC, the marginal abatement cost, and future consumption. So here is a story that would generate a negative correlation. So going to a result where the growth rate of carbon price should be smaller than the interest rate. So the story is, suppose that the main source of uncertainty is technological. Okay, we don't know whether we will get those innovations that will allow us to store electricity at the massive level at the low price. We have no idea, and maybe yes and maybe no. So how this uncertainty should affect the growth rate of optimal carbon price? Well, in this situation, you see, if it happens that we have a strong wave of green innovation, the marginal abatement cost will be small in the future, at the same time that we will not have to spend too much to decarbonate our economies because those technologies will make the cost relatively low. So you see, at the same time, we will have a large consumption, okay, because no much effort to organize the transition, and a small marginal abatement cost. And you see this negative correlation between the two, and that justifies having a small growth rate of carbon price. In fact, a growth rate which is even smaller than the interest rate. But there is another story, and Lydia, that's my next slide. The other story is there is another source of uncertainty, which is growth. And if the main source of uncertainty is economic growth of TFP, you know, put yourself in the situation with the marvelous scenario of strong growth of the economy for the next 30 years. Now, you see, in that case, in the business as usual, emission will be large, and therefore we will have to abate more. And because the marginal abatement cost function is increasing, the marginal abatement cost will be larger at the same time where the consumption will be large. And in that case, you have a positive correlation between the MAC and consumption, and that justifies having a growth rate of carbon price which is larger than the interest rate. So there are many slides now that I will not cover that describe the calibration of this two-period model I presented earlier. So Lydia, I want you to go to the slide where I have a first picture, a first graph. No, not this one. Okay, go ahead. No, go ahead. Okay, well, this one. So this one gives you the Monte Carlo simulation, because I solved the problem numerically, having, you know, macro catastrophe in order to have a relatively small equilibrium interest rate and a relatively large risk premium compatible with what we observe on the market. And you see here that there is a positive correlation indeed between consumption and marginal abatement cost, and that justifies my next slide. And I will finish here. So I end up in this model where, you know, the optimal growth rate of expected carbon price is 3.7%. Okay, so you see it's larger than the risk-free rate, which is here around 1%. Because the income elasticity of the marginal abatement cost is positive. So my conclusion, if you can go to the last slide, Lydia. So my conclusion here is that indeed there is uncertainty about the future, how the European economy will look like when in 2050, when we have a zero net emission, this uncertainty justify using a growth rate of carbon price which is larger than the risk-free rate. So we should violate the Ottmar rule for the reason of a positive correlation between the marginal abatement cost and consumption, which means that given this positive correlation, you know, the worst scenario in terms of energy transition will materialize in the good state in the good state of nature. So there is no big deal. I mean, there is a reason to postpone to the future some of the effort, but not so much. It's 3.5% the growth rate, which is much smaller than what I observe as recommendation made by experts to government in terms of how to allocate our efforts of reducing emission over time between today and the future. So the end message is we procrastinate. If we really take seriously the 2 degrees Celsius or the 800 gigaton of CO2 intertemporal carbon budget, if we take that seriously, we should do much more than what is recommended in the UK and in France in terms of reducing emissions today, and so a much larger carbon price than what is recommended in those reports. Thank you very much. I've been too long, and now I switch to Rick. Rick, I give you the floor. You control and moderate the discussion for the next 20 minutes. Thank you very much.
Thank you very much, and thank you all three for wonderful presentations. There have been a lot of questions in the chat. We have not much time, so I think I'm going to order them in the following way. We first get some questions from Maureen Cropper, which you've got mostly on the social cost of carbon. Then some questions on Christian Gollier, who has an alternative approach looking at these 2 degrees targets. So it's a what is cost efficiency approach, and then we'll broaden out to the many questions that have been asked to Michael Greenstone. So we do a slightly different order in that way. And of course the others can chip in as well. So I will collect questions because we have very little time. So coming to Maureen's thing first, there's a question by so I will collect a few questions and you answer them all in one go. So Emily Blanchard, of course, likes your paper very much, and she says, what specific implementable policies can a country use to bring the local market price of carbon towards the social cost of carbon, and also how does it need to change in the open economy? Is a carbon border adjustment enough, and what are the views on that and the work you've been doing? So, and then there have been other questions for you as well. So there's the questions, so they're a bit mixed up in the thing. So Louis Gonzalez asked the question, well, basically, how often do you have to update these 4 steps? You have to update every 5 years? Do you have to update them every year? There's some thoughts or recommendation that would be useful. Then there are quite a few questions. I particularly think of one question by Jesus Ranzulo, and who talks about the way to cope with these damages. And then other people have also mentioned the lack of tipping points, that these really can blow up the cost of carbon. How come we haven't looked at it? But I suppose the key question underlying those questions is, why did you use the Nordhaus damages? Because you started rather, with the Climate Impact Lab, which Mike also talks about. And these have, if I remember, their Nature paper, have much higher marginal damages. So then these costs of carbon may be much higher than the $51. I think that's probably the most important question to have an answer on. And then finally, Stephanie Engel say that the social cost of carbon is basically based on marginal effects. Whereas, so how about these tipping points and cascading tipping points? Thomas Lonczek also has done work with Kai in the JP, which also makes that point that really can blow up, not by 20 or 30%, but by many factors. So Maureen, the floor is yours.
Okay, thank you very much. I'll answer them rather in the order you stated them, Rick. First of all, in terms of policies to bring the social cost of carbon into a carbon price, I would say, obviously the easiest thing to do would really be to implement a carbon tax. In the United States, as Michael pointed out, we have great aversion to carbon taxes. I'm afraid that's unfortunately the case. And in terms of, at least in the United States, this happening, I'm not very hopeful of it, but I do think certainly this could be done. I mean, I think that's the easy answer to the question. I think the difficulty is political. In terms of the question of how often would you want to update these estimates, we had recommended in the NRC panel that this be done every 5 years. And there, I mean, obviously there are changes happening all the time in terms of the literature, but when you're setting out numbers or schedules of numbers for policy, you can't do it every year. People need to adjust up to them, especially if they are being used to evaluate policies, as we do in the US using benefit cost analysis. So that is, I would say, every 5 years. And I also saw questions in the chat. I mean, the reason nothing was done from 2016 to 2021 was that Trump just disbanded this group, raised the discount rate to 7%, said only US damages counted, and the social cost of carbon plummeted to a couple of dollars, unfortunately, during his presidency. In terms of tipping points, clearly these are important. There is the recent paper by Dietz and Wagner and others that tries to actually quantify the impact of 8 different tipping points. So this is a tough problem. You're right that really what's been done so far is just to look at the impact of marginal changes in CO2. So incorporating tipping points is difficult, but I applaud Dietz et al. For their recent efforts. The question about the Nordhaus damages. So let me just say that the effort at RFF, which produced the numbers I showed, really was focused on basically 3 parts, or really the first and last part of the calculation. Working on the socioeconomic scenarios and their probability, working on discounting, and then updating the climate portion of the analysis. They really did not have the bandwidth, quite frankly, to put in estimates of damages. I mean, it's a huge literature. One could certainly draw on work that Michael and colleagues have done in terms of the estimates for mortality, for energy, and so forth. Doing this was just, quite frankly, beyond the scope of the project, which was released on September 9th. So I think this is, the next thing to do, and I think it will be done, but it is something that takes some time and resources. So I'll stop there.
Yeah, just one final point. So there was this question also by Catherine Sanchines and by another person. So the implementation. So you could think, is the idea under Biden that this carbon price will be implemented for all sectors, for all types of measures, so that there are no, the kind of bang per buck, how much cost reduction you get, all of that is equalized throughout the United States economy? Or
if only. No, what will happen when the social cost of carbon is updated? This will be these will be values, and it's a whole schedule. These will be used in actually evaluating, for the most part, non-price methods of reducing emissions. Some of which, alas, you saw on Michael's slides. It would be my fondest hope that this would actually be implemented in the form of a carbon tax. But what will happen is that these will become official numbers that will be used in what we call regulatory impact analyses, evaluating carbon policies. And I should also say that the states in the United States also do a lot. And the new social cost of carbon will have an impact on policies that are being implemented at the state level.
Thank you.
I'll stop there.
So we come now to the presentation of Christian Gollier. There are less questions, but it was a more technical paper, I mentioned. But one of the questions is by Philippe Fausto, and he asks you to consider the green paradox. So more generally speaking, I suppose a big insight of your paper is that you say there's a lot of, the IPCC has 8% growth of carbon price, the UK 50% growth of carbon price, so a lot of it is postponed. So the Philippe Fausto question about the green paradox can be supplemented with the question: is your analysis missing the politics? Because there may be a reason why people shove it to the future. Anyway, your answer on that would be very useful.
Yeah, well, you know what, Rick, you are probably better placed than I to answer the question about the green paradox. Huh?
Your paper.
Well, yes, indeed. If we announce a very large carbon price in the future, that's a big incentive for resource-rich countries to flood the market today before it's too late. So yes, this is not taken into account in the model, and it's an issue. So second question: why do we see all those well, politicians promising a lot in the future but not doing much today? Well, that's procrastination. I mean, they want to be reelected in a world where many people believe in this utopia of an happy energy transition. It's very hard for politicians to explain at the end of the day, you know, you will have to pay. So it's better to postpone the effort to the future. And well, that's the problem I raise in this paper, is that it's not only politicians. It's also the case that our models, our modelers, using integrated assessment model, where they accept to have a schedule of reduction of emission, their way of planning this reduction of emission that generate this outcome of having smaller carbon price today but very large carbon price in the future, they accept to play the waiting game, and that's what I don't like. I understand the politician cannot do much, but I have a problem with the economists that come out with recommendation that where obviously the intertemporal allocation of effort is not optimized, is not efficient with respect to the maximization of an intertemporal or intergenerational welfare function. Thank you.
Thank you very much. There have been many questions from Michael Greenstone, so I'll try to do some justice, but I may come back in the second round to you, Michael. So some of them are anonymous, so then I will, it's not me, but it's them, there's some anonymous person. So one of them asked them, can you give a bit more information on what you assumed about these natural gas supply ratios when you're discussing about these backup technologies? You know, one of your backup technology was that. Another person says, how important is that countries operate on climate policies if we view the climate change problem as an energy problem because of the diverse regional context of the energy system? Is there a risk of running into a global piecemeal problem? Also, how do you view the expectation on developing countries to set a net zero target? So putting it a bit more precisely, or in addition to that, you could ask yourself the question, I mean, when I read to you that I think we'll be pilling around with marginal cost and marginal prices, pricing is not enough. That's a message I get from you. But I wasn't so good about your son's question, what should we then do? So you came up with kind of internalizing the health costs, but do we need huge, can we just get away with just giving them money? Or do we need to think about transfer of technology to developing countries? Do we need to think about, what do we need to do and how do you do it? And who is going to do it? Do we leave this to the Bill Gates? Do we leave this? It's a similar issue, I suppose, to the way we're not having dealt properly with the coronavirus, that we need to get the vaccines in those countries. We need the technology in those countries to help it. But I want to hear your view on it because you're an expert on that stuff. So you will be good. Then there are more questions. A question by Jesus Ranzulo. He would like to hear your views on creating positive market incentives globally to make developing countries increase their will to accept non-polluting sources. That's very similar to what I just mentioned. There's a lot of hope about the possibility of gas to replace coal in many Asian countries. And Renzola would like you to talk about whether you believe this is a first step or to at least initiate Frankenstein modules like the one you've shown. so maybe more precisely, how long is this window of gas and should we use that gas opportunity at the window? It's only a temporary solution, a temporary thing. Should that be used more for the developing countries than for developed countries? And a question by Emily Blanchard. Again, thank you for a great talk. Could one do a back on the envelope calculation of the form? How much would it cost to subsidize all new energy projects in developing countries so that renewables have the same private cost as fossil fuels, absent externalities of the carbon tax? So a kind of ballpark figure. There seem to be a number of people like you. Have you thought of that, or would you come up with something like that? So an order of magnitude price tag for this kind of global subsidy program. So these are all questions like how we can get the developing countries across the line. The last question I have for you, I'm sorry there's a large number of them, it's because your topic was a bit broader, and because it's very interesting, is a question by Nico Jakola. And he says you compare country average, but there's substantial inequality within countries. So you've compared inequality across countries, and you made it very clear, although but there's also a huge inequality within the countries. The wealthiest in each country emit much more carbon than the poorest people in any particular country. So carbon pricing might hit the most, the wealthiest the most. Any views on revenue recycling that needs to be done and things like that? So basically the question is about within country heterogeneity. Michael, I know it's a lot. I could give you the next 3 hours, but try to do it.
Okay, I think I have 2 minutes. So
well, no, you might have we go 5 minutes longer because you were naughty, so you get an extra 5 minutes, 5 minutes extra.
Yes, okay.
We may lose a few people on the way, but I think it's worthwhile to hear you.
So I'll probably need some refreshing of the questions along the path to make sure I actually get at least 50% of what you asked. So let me start with a super easy question. How did I build the Frankenstein plants with natural gas backup? I just took their fraction of time they operate, which I think in the US for wind is maybe 30%, and for solar is maybe 25% of the time. And then I brought them up to operating at the rate that fossils operate, which is I think 90% of the time. And I filled that in with a natural gas peaker plant. So that's what I did. It's a Frankenstein plant. It's a crude assumption, but I think it's informative. Developing countries. So first of all, Emily's Blanchard's question was terrific, and I felt dumb for never having done that calculation before. Like, how much money are we talking about was her question. So I've already emailed my RA, and we're going to start trying to dig away at that and come up with numbers. So thank you, Emily. But, you know.
Well, let's applaud the RAs.
That's right. What do we say about developing countries? So the first is, I think, Maureen put the Ramsey equation up for the optimum discount rate. That irritating G term is there, the growth rate. I think what that says, another way of saying that applying to developing countries who have very high growth rates, is they have very high discount rates. They have very high discount rates because they're desperate for consumption today, not consumption tomorrow. So I think their social cost of carbon, because of that, is probably very different than what we would calculate in the United States or Europe. And I think so. It's just a kind of technically way of saying, I don't think it's going to be easy for them, likely for them to see that a very robust carbon price is optimal for them. But what I do think many developing countries are missing is the horror of particulates air pollution. And it is, the average person in India is, according to my estimates, is living 5 years less than they would if India met the WHO standards. And should energy prices reflect just the damages from regular boring old air pollution, I think that would begin to tilt the playing field quite a bit, and is something that India would find in India's own interest, and Pakistan would find in Pakistan's own interest. It doesn't mean it's easy to implement, but I think that's a very sensible policy. And of course, there would be very large climate co-benefits. Emily's question and some other questions were, well, could the developed world do something, basically, pay, to be crude, pay developing countries to use low carbon energy sources over and above putting a pricing particulates? And of course they could. And of course, I think the politics of that are horrendous and very, very hard for people to think that they're going to get reelected. Shipping bags of money to Pakistan or Bangladesh or India or sub-Saharan Africa for them to consume different kinds of energy when we can't even get it together to do it here. What I do think is investing in R&D and that is a way to transfer resources. And until this fundamental cost differential is gone, this, again, it's the third time I'm going to quote Marty Weitzman saying the same thing. This is going to remain a problem from hell. And so I would be just shooting as much money as I can at the wall on R&D to try and change the basic economics that make those energy markets so painful and make this.
So Michael, if I may interrupt, so in a sense, there are three externalities. So there is the global warming externality. Yeah. There's a technological externality to do with this learning by doing in renewable energies, and there's a chicken and egg type externalities, like these network externalities.
Yeah.
But in a sense, we need some action, particularly on these latter two. The developed countries can do it themselves, but we might need to help them to develop. And then the fourth thing is not an externality, but it's just a huge income inequality issue.
So I think, if I were to try to be optimistic for my son or daughters, it's in the neighborhood of, I think there's some paths for policy that don't look like running directly into the wall. There was someone asked that you mentioned, I enjoyed the question, Michael, you big dummy, you're only talking about inequality across countries. What about inequality within countries? And, so let's just take everything I said and make it harder by recognizing the challenges of inequality within countries. I mean, we're in the United States, a senator from West Virginia who I think made $500,000 a year, or made $500,000 last year from his ownership of a coal company, is incredibly pivotal figure in U.S. climate policy, and the inequality and he is also from a very poor state, and within the United States, inequality within country, of course, is very, very important as well. So I know you asked many questions. I probably answered.
But this is fine, Michael. Thank you very much. So before I close, one general comment. I think all of you three end up with saying, well, politics is an important point. I mean, put it in my own words. Like Maureen, you said if only we could have the same bang per buck everywhere, but if only, you said that's a political issue there. Michael, you said the thing with this coal. If you've got kind of politicians in mind who benefit themselves from the coal, that if it's very difficult to compensate those people, if particularly if you don't have a good income tax system in developing countries, so then the politics is important. And Christian's thing was also this case that we want to recommend slower growth, more upfront action, but then these guys need to get elected. So I think in all three of us, one of the messages I get along with it, we need to think much more about the politics to get our advice across the line. But thank you very, very, very much for your presentations. And the last closing word I give to Christian Gollier as the organizer of this session.
Well, no, thank you very much. That was an excellent fourth CEPR EAERE webinar on climate economics on a very hot issue of the level of carbon pricing. Of course, there are issues related to implementation, and we had some debate on that, but that's probably a topic for one of our next webinar. Thank you very much, and thank you all, Rick, Maureen, and Michael, for your contribution today.